Welcome to The Explainer. Today, we're diving into the world of some real unsung heroes. These simple but absolutely brilliant devices that keep our entire electrical grid from flying blind.
Think about it. Our modern lives are powered by this massive electrical grid, and it's operating at incredibly high voltages and currents. We're talking thousands of volts and hundreds of amps coursing through the power lines you see every single day. And that power creates a huge challenge. I mean, how do you even begin to measure it directly? You can't just hook up a regular meter to a high voltage line, right? It would be instantly vaporized. So, what do you do?
Well, here's how we're going to break it down. We'll start with that high power problem, then we'll meet the transformers built for the job. We'll look at the two main types, see how they're actually put together, and then really understand their crucial role as the grid's guardians. Okay, so first up, let's get right into the problem itself, this massive challenge of measurement. See, here's the thing. The instruments we use to measure electricity, ammeters and voltmeters, they're pretty sensitive pieces of equipment. They're designed for low power. If you hooked one up directly to the grid, poof, it would be completely destroyed in an instant. So how did engineers get around this? Let's meet the transformers, a really elegant solution to a very dangerous problem. And this is it, the instrument transformer. It's just a genius idea. It doesn't actually measure the power directly. Instead, what it does is it perfectly scales it down, creating this tiny, safe, and exact replica of the high voltage or current. It's a miniature version that our normal meters can handle no problem. And that brings up a really crucial point. They have two jobs. As this quote from GE Vernova points out, they don't just scale the power down, they also create a vital safety barrier. They completely isolate the dangerous high power line from the people and the delicate equipment that are monitoring it. Now, these instrument transformers aren't a one-size-fits-all kind of thing. Nope, they come in two main flavors, each one specialized for a different job. First, you've got the current transformer, or CT. And, as you probably guessed from the name, its whole purpose is to measure current. Then you've got the potential transformer, or PT, which is designed to measure voltage, which is also known as electrical potential. And how they work is beautifully simple. A CT might take a massive, dangerous current of, say, 400 amps and shrink it down to a standard, totally safe 5 amps. A PT does the exact same thing, but for voltage, stepping thousands of volts all the way down to a familiar 120 volts. What's really cool is you can even see their different jobs just by looking at their circuit symbols. Notice how the CT symbol looks like it's looping around the wire, while the PT symbol connects across two lines? That's a great little visual clue for how they're physically used. And how they pull this off all comes down to the wiring, or what engineers call windings. A current transformer's main winding has very few turns. In fact, sometimes it's just the main power cable itself passing right through the center one time. A potential transformer, on the other hand, its primary winding has tons and tons of turns of fine wire to handle that super high voltage. So, that's the theory. But what do these things actually look like? And more importantly, how are they really used out there in the real world, on the grid? A lot of current transformers look just like a donut. And this window design is so simple and effective. The main high-power cable, the one carrying hundreds of amps, just goes straight through the middle. That's it. That single pass acts as its primary winding. And this diagram shows their jobs perfectly. The CT is connected in series right in the line with the load. Think of it like a single link in a chain, measuring all the flow that goes through it. The PT, though, it connects in parallel, across the line, kind of like you'd use a voltmeter to check the pressure between 2 points. So what happens with these safe, scaled-down signals they create? Well, they feed all the critical devices we rely on. We're talking ammeters and voltmeters for real-time monitoring, the watt-hour meters that actually calculate your power bill, and this is a big one, the protection relays that act like super fast circuit breakers for the entire grid. Okay, let's just zoom out for a second and appreciate the massive impact these simple little devices have. This is where you really see why we call them the guardians of the grid. When you boil it all down, these instrument transformers do 3 simple but absolutely critical jobs that keep our entire power grid from basically descending into chaos. First, they keep people safe. That's number 1. Second, they make accurate metering possible, which means you get a fair power bill. Without them, the power company would just be guessing. And third, they are the eyes and ears for those protection relays, the things that spot a problem and prevent a catastrophic failure before it even starts. So at the end of the day, that's what they are, the unseen guardians. Without these humble, brilliantly simple transformers, trying to manage our vast, high-power electrical grid, well, it wouldn't just be difficult, it'd be pretty much impossible. And there you have it, the story of the unseen guardians of our electrical grid. It really makes you wonder, right? What other simple, brilliant inventions like this are out there, hiding in plain sight, just making our complex world work every day?